Yes. All right. Bum, bum, bum. So that last problem on that differentiation worksheet, the function, what was the function again?
X cubed plus 6x squared, which is 63x plus 8.
63x
Plus 8.
plus 8, like that? Mm-hmm. And it said find all places where this function has a horizontal tangent line. And what would that mean?
That's the slope is 0.
This happens a lot because again, so many functions, whatever they represent. I mean, obviously, like profit would be an easy one. I want to find where the profit is maximized. That would be where it would have a flat or horizontal tangent line, right? So many problems involves finding where those peaks and valleys are. It's a very common thing to do is to take the derivative, and what would the derivative be?
Minus 63.
And then I set that equal to 0. And what's the first thing I can do there?
Divide by 3.
You divide by 3. Yeah. What's that? 21. And 21. The only. Yep. So x equals.
X equals minus 7.
All right. And the question says find all.
Places where the tangent line would be horizontal, all local min and max.
Yeah, good. I like it. And the local min and max thing we're going to talk about later, but it kind of makes sense. When it's horizontal, it could be one of three things. It could be this, it could be that, or it could be nana. You guys get what I mean? So it could be either the highest point in some area, the lowest point in some area, or just where the thing temporarily rests. Oh God, oh God, oh God. So it kind of tricks us. You with me? A little bit? Alright. So that's those are where those are located. At what points does it happen? At what points?
You plug X back.
Yeah, put X
Where?
back into the original.
Beautiful. If you plug it back in here, I know I'm going to get 0, because that's what we got them from, right? So, yeah, I would plug. If I wanted to know where the points were, I'd plug -7 and plug back 3 back in and get the points. So, like, whatever those are. Cool. How's that? So we see that a lot. Find where the tangent line would be horizontal. It relates to these situations. These two are extremes, and that one's just a, kind of a tricky little dude. You gotta look out for that. Okay, maybe. All right. So, any questions from homework? I just wanted to. I knew I left something undone. I had to get it done, so I could sleep at night. Any questions from homework? Yes.
58.
58 where? Oh, yeah. Blah, 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 blah. Oh, so 58 is no work, all interpretation. Which sometimes some people hate. Like, give me something to work with. Too bad. So in this case, let me see if I can set this up. Quantity Q is the quantity of fabric. This is 58 section 3.2. That's the one you're talking about, right? The one about the fabric?
Yep.
Okay. Pretty sure there can't be a lot of fabric problems. In yards, that is sold as a function of the selling price. So P is the selling price in dollars per yard. So it's not just the price; it's dollars per yard. It's a rate. Blah 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 blah. Then the total revenue earned with selling price P. Oh boy, this is a big old setup. The revenue you can earn if Q is a function of the selling price Right? And then I think they... So it'll be the price per yard times the number of yards. Because Q is a number of yards. Right? So that kind of makes sense. So if P actually represents the price per yard, I multiply that by the number of yards and I get the total money I'm pulling in. Then I get my total revenue. This is all given to you, by the way. Right? I'm just copying down what they give you. What does it mean to say f of 20 equals 10,000? Oh yeah, let me say that is sold. So the quantity of fabric that's sold is Q, and Q is a function of the selling price per yard. You with me? So what does it mean to say f of 20 is 10,000? What would 20 be?
That's the price, the amount of dollars per yard.
Beautiful. That's $20 a yard. So when you set the price to be $20 a yard, I can expect to...
Make $10,000.
No. What's f of P?
Oh,
It's Q. What's Q?
Yeah, the amount of fabric.
So I would expect to sell
10,000 yards.
10,000 yards of the fabric. So my good friend Sean, he was a financial analyst at Dell, and now he's working for American Express, and he makes a lot of money, but he's also got like 6 kids, so, you know, it's gone. But he does this. He's a financial analyst, and what they do is they try to tweak selling prices, or they give, or try to tweak the rates and so forth, so that they can get that maximum profit for the company, right? Oh, that sounds great. That's so when I'm at 20, this is not analyzing that. Yeah, this is just purely. This says when I set the price to be $20 a yard, I sell 10,000 yards, right? So then the next thing is, what does this mean? This is the more interesting question. What would F prime be? What is F? What units does F have?
Yards.
Yards. And when I say F prime, what am I actually taking the derivative with respect to? The price, because that's the variable, right? So a better way to write that is the other way that we haven't really used much of that today. I'm going to try to use more often. df dp. Well, that would mean the derivative of the F with respect to the price. So it's a little more explicit than just saying prime. You with me? And the reason this is preferred, and I think I said this last time, is you can analyze the units easier. So what units would be on this thing? Yeah, this would be yards per...
dollars per yard.
Price per yard, yeah. So it's kind of weird. It sounds very strange. Yeah, I guess we can just say, you know, like this is price per yard, but it's dollars basically. So if I got the change, so as I change my price per yard, this tells me how what's F represent again?
That's the yards.
That's the amount. So this would indicate that wherever I am, if I change my price, then the amount that I'm going to sell is going to change by something. And so what does this negative 350 mean? If I change my price, let me see if I can.
The rate at which you sell.
If I change my price by 1, because what is this over? 1. So a good estimate for where I am. If I'm at $20 per yard, if I increase the price by $1 a yard, I'm going to sell
less.
350 less. I'm not going to sell negative yards. That'd be really weird. This is anti-miter carpet or something, right? Don't step it off. Sink into it. You know. Sorry. So this is the change in the amount that I'm selling would be down by 350. So what would you estimate? How much would you estimate I would sell at 21? What would you estimate that to be? Put it all together. So right here, this tells me that if I change the price by $1, that the amount of yards I'm going to sell goes down by 350.
9,650.
10,350.
It goes down by 350. goes down by 350, so I would have sold 10,000 at 20. If I change that by 1, how does the yards change?
By 350.
It goes down by 350, so you would have sold 10,000, now you're going to sell,
96.50.
96.50. That's better. Why is that really? Okay, so what's happening here is when you're in business and you're doing these things, you have stuff called marginal cost and all that kind of crap. But what's important for us right now is if I'm at the point where if I change my price and my change line's negative, that's what that's saying there, right? At 20, the derivative is negative. Which means if I change my price by 1, I can estimate that I'm going to sell 350 less. Which makes sense. If I increase my price, people might go somewhere else. They might decide suddenly they don't need it. Right? Mm-hmm. So there's always that give and take between the two. If I increase my price, I'm making more money for every yard I sell, but I might sell less yards. So there's some kind of somewhere there's the two kind of give me the highest point. Maybe. I love this problem. My God, because you really have to stop and think about what does the derivative mean, and where do you start? You think about units. Units tell you the physical rate of what's going on. I love it. So the second part to this problem deals with the revenue. So here's the revenue. How do you do this? Okay. How? What rule do you need to use?
So that's dr over dp.
Yeah, so you could use dr, dp, I like it.
And then so we.
That doesn't really help you do it. I mean, here's RP. What do you have to use? What is this? This is a product, so you probably have to use the product rule, which says what? P prime
times
F P
plus F prime.
P F prime of P. I like it. Whatever way you want to write that, I don't care. It's multiplication. Cool. So that's the first step in part B. And then they ask you to figure out what this is and interpret it. I like it. So that's all I'll say about that. So with part A, we kind of talked about. Part B, that's the first step in part B. And then you got to go a little deeper into it. So give that a try. I know it's painful. You step away from the number crunching and actually think about what the hell you're doing. That is painful, I know. I've seen it. Anything else from homework?
Oh, 42. Same section.
Oh, the instructions just make it sound like it's going to be horrific. They say if you're given that g of x is this, find, what does this mean? But first off, this notation, what do you think this means? Alright, so you leapfrogged over the answer to my question, if you're going to say that. You do have to use the quotient rule if you're going to take a derivative. But something I haven't said explicitly yet, what's that mean? Let's just say g. G prime would mean what?
One derivative.
The first derivative. Then the second derivative, right?
Yes.
Third derivative. Can you imagine at some point we're like, we can't have g prime, 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 prime. At some point we gotta go, alright, we're just gonna put a 4 up there and say everybody understands that's the fourth derivative, fifth derivative. So this means the nth derivative. So the question tells you what's going to happen. There has to be a way to write this dependent on n. There must be a pattern that you will see if you do all of these. Not all of them. Do like 4 of them maybe, or 3 or 4, whatever you can see the pattern. So let's try 1, just make sure we can do 1.
Derivative of the top
Yeah, derivative of the top times the bottom.
minus
The top times the derivative of the bottom. All over. And what is e to the x squared? E to the 2x. And what do you get on top? You get,
Yeah.
yeah, good. E to the x minus x e to the x over e to the 2x. And what can you do with, I don't know if you guys, 1 e to the x can cancel. Get 1 minus x over e to the x. All right, I'll let you guys soak that in. They all have an e to the x, so I can kill that from everybody because it's division. All right, that's all I'm going to do. Now you do this. What does this mean?
Take another derivative.
Take a derivative of the derivative. I like it. It's the derivative of the derivative. And that's the derivative of the derivative of the derivative. No inception. Don't bring that up. Where am I? Who's spin? Come on. Do your train? No, stop it. If you've never seen that movie, you're like, what is happening? Is that cool enough for that? I mean, that's... So when you read it, you feel like, what am I supposed to be able to do here? Well, it's what math is about. It's about finding patterns. So do the first few, and then you should very quickly see a pattern develop. Maybe you'll see a 2 somewhere. Maybe you'll see a 3 somewhere. So then for the nth one, you can just put an n there. Yeah. Maybe something like that will happen. I don't know. Okay. Anything else from homework that I can do half of for you? I just get this feeling not everybody's tried that problem. I'm not going to do more than that. Okay, all right. So, I've got the practice test I'm going to give you in a minute here, in a little bit. I've got a handout on chain rule, but I want to first talk about chain rule. And very, very first thing is, why do we need chain rule? So let's see. Remind me real quick. F prime here would be what?
2x.
Right, yeah. So if I erroneously believed, ooh, I like that word, so this is erroneous. Good Lord, Jeff. If I thought that this worked the exact same way, well, let's check it out. And no matter, so for a derivative to be true, any simplification I can do to the original function has to come out to the same derivative. Does that make sense? The derivative of a function is a thing, period. I don't care what I make the original function look like.
What about 3 that is inside?
Thank you, John. This is a wrong thing, right? So we're going to investigate why that is needed. You with me? So hang on. This is wrong. In fact, if you've written this down, go ahead and do like that. Just to be sure, all right? So let's do it the right way. Well, first off, let's investigate this. Let's see why this is wrong. What can I do with this first?
Oh, you can
Extend it.
Yeah, so what would I get?
9x squared plus 6x plus 1.
I like it. And what would this guy's derivative be?
18x plus 6.
And so here, I thought it was twice 3x plus 1. What can you factor out of this?
6.
So the actual answer should be 6 times 3x plus 1. Really absorb what I'm saying here. Do you guys understand what's going on? If this was the right way to do this function, the derivative should have come out the same way after simplifying the original function. It's got to be true. Just because you make a function look different, the derivative can't suddenly fundamentally be different. It's got to be the same freaking derivative because it's the same freaking function. Right? This one I know is right. We know this is right because it's built off of rules that we know for sure is right. So our guess on this rule must have been freaking wrong. What am I missing? What is this missing to be this? John's the inside. So now think about it. When I take a derivative, that tells me what? The slope. So it tells me how quickly it's going up or going down as I change my x, right? So x squared has a certain speed it's going to travel at because of the square. It's going to be going faster at some points than a line would in x to the first power because of that square, right? Do you guys understand what I mean by that? But 3x plus 1 is going to be going how many times faster than this? 3 times. It's got 3 times the slope. So the overall slope of the result should be a combination of this guy's speed and this guy's speed, right? Does that make sense?
Yeah.
So what I need to do then, what makes sense for this is I need to take the derivative of something squared, so the 2 would come down, but then I have to multiply by the derivative of the inside. So I get the overall speed, right? How are we doing there? So if I was in a kayak and I was rowing at 2 miles an hour, but the freaking river is going 5, aren't they going to kind of like combine with each other in a way? And this is not exactly that, but you understand that the rates have to somehow affect each other. What was the other? No, that's later. Okay. So that's nice for like a hand waving kind of, it looks like this should be true, right? Let's do one more of these kind of things here. What if I had this? And this will really hammer home the point. Yeah, I like it. Well, let's see. No, let's do this. Sorry. That gets a little too weird. There we go. Okay. So very quickly. In both of these, there's what can be called an inside function and an outside function. So for this first one, what would you say the inside function is? 3x plus 1. And it's inside what function? It's inside the squared function, right? Yes?
Is it sine 2x? Answer.
We're going to find out. I like it. But we're going to get there. All right, you ready? So what's the inside function here? Sine, and it's inside squared. I like it. All right. So the wrong way to think about this is that it's going to act just like a squared, and the 2 is going to come down. That's the wrong way. That's not going to be the way it works. So what's the right way? Well, let's do it the only way we can. What's sine squared? Sine times. No, come on. Sine squared is sine times sine. It's what the 2 means. You got 2 of these, right? All right. I like it. I love how you guys are just waiting for like the trick or something. Come on. No. So how do I take this guy's derivative? I have to use product rule. I like it. So derivative of sine is, all right, let's just do the whole thing. Right. Sine x prime, sine x, right? Plus sine x prime. What's sine x prime?
That's cosine. That's positive cosine.
And the way to remember it's reverse alphabetical. S goes to C, it's positive. C goes to S, it's negative. I don't know if you like that. If you like it, great. If you don't like it, come up with your own thing. All right, don't make me do all the work. So am I not going to get sine, cosine twice? We're finally catching up to you, John. So does that make sense? I mean, sine, cosine plus sine, cosine, which is 2 sine, cosine, and hopefully you guys remember that you can rewrite 2 sine, cosine as sine 2x. Very interesting. But forget that for a second. You could if you wanted to, but I want to look at this because I can compare it. What is this guy missing that this guy has? Cosine, which is how related to the inside function. It's derivative. So the rule we seem to be coming up with is if I have a function, and let me just write this. Sometimes it's better to write this what it really means, right? Put in the 2 in the middle, it's just a little thing so I don't have to draw the parentheses. So the rule seems to be take the derivative of the outside function and then multiply it by the derivative of the inside function. So it's the whole idea of they each get a turn. Didn't I tell you that was going to repeat again? So the outside function gets a turn, and then the inside function gets a turn. And why do we call it chain rule? Because they're like links. If I had another function inside of this function, oh yeah, then I would have a couple links on the end, right? You like it, I know. Again, this is just feeling out why chain rule has to exist. Now we're going to very quickly prove chain rule. I love Thursdays. So the way we prove anything, and you might just want to watch this, I don't know. It's up to you. If I want to, so what I really have is a function inside another function like that. Is that cool? And to figure out its derivative, if I don't know, I have to go back to fundamentals, and I have to use limit definition of derivative, right? What goes here? Well, what always goes on the top? You take the function you're talking about and you plug in x plus h.
X on H. Ah.
H. I like it. Cool. Sorry. I just had to. I'm sorry. You're sitting in a bad area. Crack your neck. It's always like, oh my god. All right, here comes. You know something weird's going to happen, right? Because this looks like there's nothing. There's not a damn thing we can do here. I hope you understand. That's just funky as hell. What the hell? It looks like nothing. So what we do is we do something that I would never think of. Maybe. All right, how can I just write that there? Because I'm going to immediately cancel it out. All right, let me let you absorb that. I know, that's one of my favorite things to say. So many guys are like, absorb that. No, don't do anything weird. I'm sorry. That was for me. Is that cool? It's sort of like what we did earlier, but instead of adding, subtracting, I am dividing, multiplying. So the thing that I've introduced goes away. To be completely honest, there are a few technical aspects to this that I'm not going to even freaking worry about. You might imagine that there could be some problems when I'm introducing something on the bottom that didn't used to be on the bottom, but screw those. Those end up being no big deal. If you don't believe me, you can Google the damn thing. What good does that do me? Well, doesn't this look like input? Doesn't it look more like f of x plus h? I mean, this, I don't know if you guys understand what I'm trying to say. What it looks like, yeah, what is this the derivative of? This will be the derivative of f prime of g of x. That, so what do you, normally when there's an x plus h and an x and an h, I get f prime x. But now I get f prime of this. I get f prime of that when I do that. That's the form it's in. And what's that? The limit of that piece is going to be
G prime.
Now really think about what this says. Take the derivative of the outside function times the derivative of the inside function. That's what we were saying earlier. All right, that was probably the quickest I've ever done that, so it probably made very little sense. And I actually don't quite care entirely. Because there are, like, for everything up here, there's at least 50 other proofs. And if you really wanted to, it's insane how much access you have to other proofs. It's crazy. Just Google the damn thing. So let me give you this little handout.
So when you take the derivative of the first, of the outside function, when you take the derivative of the outside function, do you leave the inside?
Beautiful,
function?
exactly. Derivative of the outside function as if this was just x. It just stays there.
And then you
I like
multiply in whatever.
So we'll do a couple more examples here, obviously. There's some worked out examples on here.
Can I get the extra one for Steven? Please.
Okay. So here's the problem. Let's do a couple of these real quick here. Here's the problem that brings tears to my eyes. Because I still have people that... so there was a problem where it was ln x equals 2 or something. And I had people doing stuff like this, or, you know, and then it became correct on the next line. But I mean, that's not what we're doing, right? I mean, or I have people that put, if it was e to the x equals 2, they just put an ln, they put an ln. I mean, what is happening? That makes it look like what you're doing is multiplying by a symbol. So, you know, I said x squared equals 4. Well, the answer is 4 times a root symbol. What? No, I'm taking the root of the damn thing, right? So does this say sine times tangent? Is that what that says?
No.
Hell no. It says sine of tangent of x. If I meant sine times tangent, I have to give the sine its own little thing, don't I? A sine by itself doesn't mean shit. Alright, so what's the inside function there, obviously? Tangent. What's the outside function? So the first step on chain rule is you take the derivative of the outside function as if that was x, and it just comes for the ride. So what's the derivative of sine of anything?
Cosine.
Cosine of that thing. Times. Good. The derivative, and again, you can write the rule. The inside gets a turn, right? So people that don't write the rule are the ones that are concerned about how do you know when to stop. When you're doing chain rule, that's one of the most common things is, how do I know when to stop doing this chain rule? If you wrote the rule, you would know when to stop. Is there an inside function here? So I don't have to do frickin' chain rule, right? It's the people that don't do this that are like, I'm continually taking derivatives. I got to take another derivative. Oh my God, I don't have to do a chain rule here because there is no inside. Well, actually, what is the inside function?
1.
X. And what's the derivative of x? 1. So we've been doing chain rule this whole time. No, sorry. It's so funny. This whole time. You never no. So this is going to be what? Cosine of tangent of x times secant squared x. So like kick ass. Oh, that's one of the newer ones, but you got to know those trig function derivatives. All right, let's do a triple nested monster. Sorry. No, sorry.